Yeah, so the it can, the title of the talk is Containers, Virtualization, and Emulation. So just to get started, emulation is a program that runs another platform's binaries. So pretty much all of our laptops here are running on the x86 instruction set. So they have x86 CPUs, pretty much everything Windows again, and most Linux computers are also that way. It's our phones that are mostly running on the ARM instruction set. So if, for example, you want to develop applications for your phone on your x86 laptop, and you want to run the binaries to test them out on your Windows computer, then it helps to have something to emulate the phone. So, for example, in Android Studio, if you're trying to run the binaries on the phone, run the binaries that would be running on the phone, then there's if any of you have worked with Android Studio, you'll see that there's a um, a window that comes up that emulates the phone. You can give it clicks and type keystrokes onto it, and that allows you to run the emulation. So an emulator is just a program that interprets the binaries that are compiled for another architecture and runs them. So in theory, you could also have an emulator that runs binaries intended for the CPU architecture that's you're running on it. And also in the Linux space, there's a program called QEMU or QEMU, and it basically it's used for that. A lot of it's pretty frequently used by people just because a lot of people don't like VirtualBox, so they'll use that instead. Yeah, it's an emulator, so you can, but also people use it just for general purpose virtualization because it is a pretty solid program. So it in some like high performance settings, it may not perform as well as virtualization, other types of virtualization. It's still pretty solid if all you want is just isolation between the different virtual machines. So it's a solid pick. It's necessary for a lot of applications, but it's not. It's also a pretty niche type of virtualization. So the one we're all probably most familiar with is called the virtual machine. So it maps instructions to the native CPU instructions. They actually, generally speaking, they take advantage of core technologies in the CPU. So for a lot of computer, or it's less common now than it was, I think, before, but a lot of times if you actually want to run VirtualBox, you might need to like enable it in your BIOS because it's needs a way to map the CPU instructions of the virtual machine to the instructions of the host machine. So there needs to be some special work done to make sure that the virtual machine isn't getting access to that stuff that it shouldn't get access to. So there's that. The Obviously I'm showing kind of the top three virtual machine pieces of software or virtual machine hypervisors. I guess I could have made the distinction between the different types of hypervisors. So, for example, VMware is a bare metal hypervisor, I think. So you'll hear the term type 1 and type 2, but I always get them mixed up, and it's more intuitive to just say that it's a bare metal hypervisor. So the VMware runs as an OS, and then you can go through its interface and create virtual machines that way. Whereas VirtualBox and Hyper-V, which I'm pretty sure the term is Type 2, where they run as programs inside of another operating system. Microsoft Hyper-V obviously runs inside of Microsoft. VirtualBox is platform independent. It can run on Linux, on Mac, OS X, and Microsoft. So you'll see relatively frequently that people might just, if they have an application that they want to like, demo you or to show you, they just like send a virtual machine disk file to you and just say, "Hey, boot this," and you can have my application. In in the previous CCDC competition, we were working with a program called Ka, and they to demo it, you could clone their repo with Git and run all the build steps, or you could just clone the VirtualBox or download the VirtualBox image and don't run it that way. Of course, it's a lot thicker than just cloning it down and doing it yourself, but it is also pretty convenient to do that. So that's more of a licensing thing than. So are you saying in ESXi versus? Oh yeah, that's a good point. Um, yeah, so obviously if you can get in the VMware hypervisor installed on your laptop, and that runs as a Type 2 hypervisor. So yeah, you're right there in that case, Max. I guess I could have had separate icons for ESXi and for VMware, like VMware Workstation. So yeah, the different types of virtual machines, they map the instructions of the guest machine to the instructions of the host machine. And for virtual machines, they need to be the same CPU architecture. So you can't run Android app. You can't. You wouldn't be doing Android development via a virtual machine. You can't, or for like ARM development, like if you can't run a Raspberry Pi, run install Raspbian on VirtualBox, you'd need some sort of emulation because Raspberry Pi Raspbian is built for ARM, not for x86. But a lot of these are nice because they have some really nice features. ESXi has some advanced features that, for example, let you migrate VMs between hosts in a cluster, so it can be really useful. This area has received a lot of development, and that's why pretty much all of us use it for one reason or another. so going so a lot of us here are also interested in containers. So containers are probably closer to virtualization in this. Well, they're their own category. So basically, containers are a method of virtualization where the various applications share the same operating system, in the same kernel in the context of Linux, and they basically bring their own binaries to the table. So if you look here on the left where I'm pointing, this is the traditional hypervisor virtual machine example. So you've got a hypervisor, which is the program that runs the virtual machines. And inside of it, there are the guest OSs. Each has its own kernel, essentially, that's running and taking up disk space. Whereas here on the left, you've got the Docker engine. So you've got them sharing a kernel and sharing some libraries. So the advantage of that is that it takes a lot less RAM. So for example, you can run a lot more containers than you could virtual machines. So that's the primary benefit of running containers. So on Linux, it works by essentially, so the Linux kernel has built into it these things called control groups that allow you to isolate certain resources based on like users. It allows you to isolate various resources from each other. So for example, you could restrict certain processes to only access certain directories or certain disks. So that lets you, what that lets you do is it allows you to create virtual machines essentially within that, because if one process can only access these directories with control groups and chroot, then that means that you can that that piece of software is essentially isolated, and it can't and it lets you keep them from messing with each other, and that's useful for when you're developing applications. You want to isolate the dependencies so you can give each piece of software its own environment to run in, and you can know that they're not messing with each other in any bad way. So Docker uses this. There's also a virtualization uh, solution called LXD that's run by the company Canonical, which runs Ubuntu, well, the most commonly used Linux distribution. So both of those have their own methods of interacting with it, but they do very similar things with the C groups and the namespaces. So that's what lets them be isolated from each other. Oh, okay. So LXC is used by LXD. So LXC is, I think, built on top of control groups and all the technologies I listed here. LXD has more built into it, and it lets you. I think I haven't personally used LXD a lot, but it's got more. So I'll just say, like, all of these solutions built on top of Linux control groups are essentially nice front ends to the same core pieces of technology, right? So LXD might, for example, have a nicer way to create virtual networking hardware and connect them to virtual machines. To be honest, I'm not too familiar with. It's been a while since I've even used LXD. I haven't. I was playing around with LXD a year ago, um, but they all have different ways of creating VMs, like configuring the hardware and then starting them running into different process models. So it's more a matter of how they interact with the creation of the resources. They all like use the same core technologies though. Yeah, good question. So I just wanted to put this in there. BSD has had something like this going back pretty far back anyhow. So they have these things called GLs, which are very similar to the Linux LXC and control groups. The, I was looking around and they don't have anything like where, as pointing out, C groups allow the isolation of these various resources. I don't think they have separate words for those those functionalities, but essentially BSDGLs do all of that. They let you create essentially a container and run it and like kind of upgrade them separately. So BSD has a lot of cool technologies like that. So they've also got really cool file systems which let you roll back. They have one called ZFS, and so what they'll do is they can have a GL, which is basically a directory that processes are running in, and then they can like roll back the GL if they want to test out an upgrade and or do stuff like that. So there's tons of cool stuff you can do with ZFS and BSD. Okay, so ZF. Oh, I'm sorry, I didn't mention ZFS. Yeah, so it's basically a file system with that is very good at managing redundant. It also manages RAID. It's very easy to add drives to it, if I remember correctly. They they have snapshotting, which lets you roll back the state of the drive to the way it was before. So it's got like boatloads of features, and it's used by a lot of it can be used for a lot of like very advanced disk management. So you could have like a humongous array of disks and and add them to your ZFS array. Yeah, yeah. So there's even a way. So basically the file system is basically I'm probably getting the like finer technology terminology wrong, but it's basically a program that acts as a middleman between the operating system and the hardware, or between the operating system and the hard drives, I should say. So a basically the drive you're working with, it has a billion ones and zeros, or I forget the numbers, but it's got a ton of ones and zeros. But how do you actually manage the blocks of the files um, as they're laid out on the silicon or on the metal of the hard drive? So the the file system manages that, and because you can't just allocate a gigabyte to a particular file and write to that as time goes on. You need to have it chunked out. So the file system does that essentially. Yeah, they've got the technology. The one thing about the BSD ecosystem is it seems like it's a lot more fragmented. For example, whereas on Linux it seems completely centered around Docker. On BSD, there are tons of different tools people will be using. Like one is called EasyGL, one is Beehive, it's kind of pronounced Beehive, but it's spelled like this. Another is IOCage. And it seems like, how before I was saying that on Linux, they're all using the same core piece of technology. They're all using C groups. In this case, they are. The case is pretty similar. They're using the same core piece of technology, and people are just writing different front ends for it. So, oh yeah, I just wanted to put this in there. There's a funny comic from Dilbert. Wally is essentially saying, "Hey, you're one of those condescending Unix users. Here's a nickel, kid. Get yourself a better computer." So, FreeBSD is the main one you'd be using on servers, but there are also other BSDs that are used. Um, One is NetBSD, another is OpenBSD. I think NetBSD is more focused on compatibility, like running it on literally everything. OpenBSD might be focused more on security. Okay, so now I'm just going to go into some of the reasons you'd want to use containers. So if you've ever kind of worked in development or worked with developers, there's kind of a split between the people who are writing the code and the people who are deploying the code. So if there are issues with the code when it gets put onto the server, and then the developer will say, "Hey, it works on my laptop," so obviously the issue's there, and then the guy in the ops team essentially says, "No, your code is wrong. Obviously it's not working. Everything's good on our end." So it helps to have the same environment on both the laptop that's being developed on and the server. So that's one of the nice things about Docker, for example. I'm just going to use Docker as the standard container example because the idea with Docker is the developer has Docker installed on his or her laptop, and then makes changes, commits changes, and then with eventually the same Docker container gets deployed on the server, and as a result, the environment's always the same, the libraries are always the same, everything's always the same. So that way, when it gets deployed, nothing bad will happen because it's exactly the same as it was in development. So that in that situation, then RAM really matters because obviously, like developer laptops, even if you've got a lot of RAM, maybe you've got 8 gigabytes, maybe you've got 16 gigabytes, but if you're like spinning up like a dozen VMs for the sake of testing out software because the software has many components to it, especially since one of the kind of, I won't say fads, but one of the things that's been in style for development has been microservices, which is using multiple different like writing software components in as small of pieces as they can be written. So as a result, you might have tons of VMs you need to run in order to be developing what you need to be working on. So it helps to be able to simulate everything on the the, the developer's laptop, and that helps to do that.
So is the developers like the RAM on the developer's computer more scarce than the RAM in the server?
Well, I mean, you can install much more RAM on you can install much more RAM on a server than you can on a laptop, especially on a lot of MacBooks, which the developers like. There is like sometimes it's soldered to the motherboard. You can't upgrade it yourself, right?
Sure, I'm just thinking that now with the trend of moving to the cloud, like on the cloud, you tend to use large boxes with lots of RAM.
Mm-hmm.
Like it's
Uh huh.
to the cloud, and it was a transition from like 28 gigs of RAM to like 2
Uh huh.
some of the machines.
How'd that work out? I feel like that would.
But as far as I know, they just optimized like all of their code
Mm-hmm.
to
Yeah,
like
that's some pretty impressive optimizations if you can use like what one tenth or like 1/20th the RAM.
yes, like that.
Yeah. Yeah. I mean, well, the thing is, a lot of the I think I know in particular, it's that's also consistent with the container way of doing things, where you might be able to, for example, upload your Docker container and have the that run in the cloud. So there are different ways of doing it. If you want everything to be in your local network, then you'd do it one way. So it all depends on what, but it all depends on the situation. But obviously, there are different use cases where this may or may not be the optimal solution.
Yeah, I'm just thinking that in this case, this actual servers do have less RAM than if it was
Yeah,
moved like
well,
anywhere else.
that's completely different because they optimized that away, and generally speaking, that's not the solution. You don't generally tell developers to write optimized code. I mean, unless you're in gaming or something. Huh? Oh, okay, no, never mind. I thought someone said something, but generally speaking, or at least we've been used to just getting more RAM. Moore's law. Obviously Moore's law isn't RAM, but generally speaking, a lot of these resources have been getting cheaper for us, so it's mattered less. It may matter more as like Moore's law becomes less of a thing. But anyway, so aren't they all the same? No, they have different ecosystems. For example, VMware is already very popular in the enterprise virtualization market, where so that's one kind of use case where VMware is very heavily used. Docker is more popular in kind of the developer space. It's got Docker Hub, which is a nice thing where people upload their Docker files, which are used for basically automating the automating the creation of VMs. So they also have different features. One pretty cool feature of VMware vMotion is it allows you to move VMs around the cluster without shutting them down. So it can be really useful if you need to upgrade something. You can just migrate the VMs off of that to another one, shut that one down, do everything you need to do, and then just kind of cycle that around. Um, Tooling. I was gonna say, forget what I was gonna say there. I'm probably gonna comment about the fact that Docker has built-in support for like scripting the creation of VMs. So I'm gonna cover that in later on in the talk, but that's one factor that Docker has. It's got its own built-in like automation engine. So as I was mentioning before, um, another component of virtualization, which isn't obviously before we were talking about the distinction between um, virtualization, containerization, and emulation. In this case, this isn't anything that's specific to any one of those, but it's still a relevant thing to the topic, and that is the automatic generation of VMs. So Docker, if you look at this kind of black background, green text area, this is essentially a script for installing Apache 2 on a Docker virtual machine. So you can use Docker as like a way of automating the creation of containers as well. It's not just the core technology, it's also got a built-in scripting system for scripting the creation of a VM, not VM, I'm sorry, container. So that's something that's very useful for developers. And there's an equivalent technology for that can be used for pretty much all these virtualization types called Vagrant. Its config files are actually written in Ruby, and it lets you automatically, for example, create a virtual machine and then set its IP address and stuff. It actually lets you configure it directly in the config files. You don't even need to make a clever script for doing it. You can just tell it what type of network you want it to have. So there are some really cool technologies built into that system as well. So there are also a lot of trade-offs. So why would you want containers? So nice to they're very good because they can be spun up really quickly because they have low RAM requirements and they're sharing the same kernel. Um, and that's very useful, like I was saying before, in software development, where you want to spin them up because if you're running a build, it's very nice for that. It's also nice for running builds in because the environment can be very clean just because you don't need to be using the same server for everything. And like I was saying before, it fits nicely with the microservice architecture whereby you're running a lot of lightweight um, pieces. You're running a lot of small pieces of code running in their own environments. So it makes very much makes sense at these like hyper web scale companies like Google. It's interesting. A lot of these sorts of technologies were developed were worked on in the early 2000s by Google, as included this comic to kind of convey what sort of scale that it makes sense. So the point where it doesn't even make sense to throw out the entire to repair the machine, you throw away entire racks of machines just because it takes too much time to spin them up. So it fits nicely. Downsides, the images still take up a lot of drive space, so it still does. Like if you want to download a Docker or an image that was generated from a Docker file, it still takes up like a gigabyte or a couple of gigabytes of storage. So it's not some like magical thing where everything only like weighs in at a few megabytes. And kind of going off of that, applications still takes RAM, or applications still take RAM. Database software doesn't like magically require less software because it's running on a lightweight, running on the same kernel as another one. So it saves on RAM from the operating systems. It doesn't magically take up less space from database. Databases don't magically take up less space. Another downside in general of virtualization in general is, well, and this isn't specific to virtualization, but it's a thing to keep in mind, is that generally speaking, a lot of the work will be done based on golden images, and these are images that you install everything on top of afterwards. So you can define an image that you'll be using, and then run you can run the have your script run the installation from them. And while that's really good, but it's good to have that sort of a thing, but you'll it's very easy for those to fall out of date if you're not careful. And this kind of goes to more of the cloud aspect that Max was talking about. It's also very easy to upload, accidentally include the wrong data inside of the golden images. Like if you have some sort of API key that's in your environment variable or something like that, then if you upload the image or the Docker file, if you upload the image to Docker or Hub or some other sharing site, then you might accidentally share your your API key or whatever you're working with. So, yeah.
Question. So, say for example, you are running a Ubuntu system that runs like dozens of containers, right?
Mm-hmm.
For example, as for CCDC computation, if you would have an environment that actually was you were given some access to the Docker containers. Say we find a problem that's outdated. Will it be able to update it from the container itself?
Um, could you say that again? If the
So, say you're given access to the particular Docker container,
uh-huh.
say as safe access, would you be able to upgrade this system without touching the original like operating system?
Well, the thing is, so in the CCDC competitions, sorry, we're already working with virtual machines, and we still, even if we had, it wouldn't be easy. No, there wouldn't be an easy way of doing that. You could you could run you could run patches inside of the OS itself, but it's just as difficult patching inside of a container as it would be in any normal OS, right? Because you're going to be needing to do work in the OS, and the major difficulty of patching stuff is making sure you don't break it to begin with. So that's the first thing, is make sure you don't break things, and that's an issue whether you're working with a container or not. I don't think having it as a container would, unless you have like snapshots or something like that, then it wouldn't necessarily make it easier to run upgrades on.
Yeah, I'm not thinking more about like and stuff. Rather, will we be able to update, say, binaries of files that are that I mean they're supposed to belong to the operating system itself. But if I want to update the binary on the container,
Mm.
will it just copy and use my local versions of files instead of some global version?
So generally speaking, doc LXC, I'm thinking from in the context of LXC, you may be able to overwrite it from the host operating system. And are you are you saying in the context of permission errors?
So
So
not necessarily well, permission errors as running the Windows regulators or Windows kind of containers or system container systems. Do they provide a way of overriding the binaries that are posted for all shared machines?
um, that's I would say that's not the idiomatic way of doing things. You can probably like hack your way into doing it, but generally speaking, the way you want to interact with them is by going into a shell into the guest operating systems and working with them that way, rather than doing something that could break the guest operating system. Yeah, so kind of I wanted to describe some of the hypothetical alternatives whereby various types of virtualization would be less useful. So, for example, if you already deploy your work using Tomcat and just upload a jar file with bundled dependencies, the state of um, the the OS that's running on there matters a lot less than it would if you were like deploying some other application, because the bundled dependencies are already there inside of the jar file. So it's less of an issue. Also, if you have a site that's working based on Golang, which produces statically linked binaries, so it doesn't depend on the libraries of the host operating or the yeah, I guess the host that's running it, then these are mitigated in the sense that you can just install them on any server, and they should work more or less just as well.
Is it using Golang?
Yeah,
Language?
yeah. The language is called Go, but the thing is that that's a strange thing to name a language. So generally, it's frequently called Golang just for the sake of it.
You said like you to all the libraries or whatever you can use and you program.
I said that when it's compiled, it produces a statically linked binary. So generally speaking, when you're compiling things with C or C++, generally speaking, they produce a dynamically linked binary. What that means is that the code, the compiled code that it produces, it depends on certain libraries. so if you so if you copy it to another machine, as long as the libraries of the original machine are compatible with the libraries of the destination machine, that's fine. But if the libraries were not compatible, then it would have issues because it was compiled on one machine with a certain set of libraries. Now it's on a different environment with a different set of libraries. So this can be an issue even for example, Python programs, because they end up using a lot of basically C libraries in on the host systems. So even on a lot of on a lot of languages that are not C, you still end up being dependent on C stuff. So that's why it's important to to look at the libraries that you're running.
So you say usually that means like is there like an option or something that set a flag
Yeah, you can
to
do.
make it static?
Yeah, you can, but generally speaking, that's not. For one thing, it's not the like kind of idiomatic way of doing things. Generally speaking, like if you go onto Reddit and like the C Reddit and talk about how you're statically compiling things, you might get a few people saying, "Hey, that's not the standard way of doing things." Generally speaking, I mean, like people have internet discussions about this sort of stuff, so I'm probably not doing it justice. But generally speaking, the way of doing things, you'll need to do work to get it working for statically linked. So yeah.
When you when you're saying about like the C library and the Python,
Hmm.
now are they like are they automatically imported or you import them like individually or how does that work?
Well, so there on in Python there are it's so basically what they are libraries you can import that are written in C. So from the standpoint of the person programming, you wouldn't really be able to tell whether or not your library was written in C or whether it wasn't, as long as you install. So Python has its own like system of importing code from C. So from the standpoint of the programmer, you wouldn't notice unless it was failing. So generally speaking, they're compiled for each OS and each both 32 and 64 and all the different architectures, and so that's something that needs to be managed. Otherwise, or at least it needs to be taken into account. So yeah. There are also, to go into what before we were talking about different methods of scripting. So there are also other ways of doing the scripting, which is also known as configuration management. So installing packages, copying config files to directories and that sort of stuff. There are also tools for doing that. The kind of most prominent one is Ansible, but there are other ones like Salt Stack, Puppet. Yeah, there are plenty of. Chef is another one. There are plenty of tools that are used for scripting the configuration of your servers as well. And also, as always, you can also do these things manually with just without virtual machines. Just install everything on your host machine, or if you don't have enough host machines, just get more. Right, buy more hardware the old-fashioned way. Yeah, so that's everything I've got from the standpoint of the presentation. Anyone got any questions or? Uh,
Is the presentation online?
it's online. I'll post it publicly, um, but it's not posted publicly yet. So I'll get you a link to that. Yeah. Okay. Well. Yeah. Thanks, guys.
I have a more random question.
Oh. Okay. Yeah. Sure. What's your random question?
Do you think that learning about databases is useful in like the general cybersecurity
Um.
field?
Well. So if you're there are always like different categories, different fields within it. So if you're interested in, for example, troubleshoot finding out the security of web apps, and that's a pretty common thing to be like penetration testing. I'd say that's a good thing to know because web apps are there is a lot of dependence on web apps on databases. And there are probably also a lot of easy ways to misconfigure them
Mm-hmm.
in because the the meshing, but the interface between the web app and the database is one that's been pretty commonly exploited. I mean, about SQL injection, right?
Yeah.
So that's basically exploiting the joint between the web app and the database. So it's good to know about the database because it's a pretty common attack vector, and it's pretty common for like the bad guys to get access to the database and then pivot and do work from there. So it's good to know about it all depends on which area of security you're going into.
Mhm.
Anyway,
Some of those courses may also take into account like permissions and stuff like that, which is not working with databases, but with the database management systems themselves. So it's kind of unique as well.
mhm, yeah. Anyway, yeah, thanks guys. That's all.